Hi everyone. This series of videos is going to continue along with the lesson on the second fundamental theorem of calculus, beginning on page 8. The goal today is to extend what we saw the last lesson about the second fundamental theorem of calculus, specifically how we can make sure that we start to understand all the different implications of having a second unknown quantity in the problem itself. As a reminder, the second fundamental theorem of calculus is the one where we're integrating in terms of t with a dummy variable, but one of the limits of integration, specifically the top one, is also unknown, which is like saying we don't exactly know where we're going to stop finding areas or stop taking antiderivatives, so that unknown x ends up becoming a very important part of the process. So important that what we realized on pages 6 and 7 is that x ends up becoming the variable in our answer and t ends up disappearing. That is a little bit strange, that idea that the dummy variable is just there as a placeholder and that it ends up going away, but that's something you'll continue to see a little bit more today. So in theory, by the time we finally get to some real practice questions, you'll have done enough examples to start to get that idea of repetition, that the t, the dummy variable, just ends up going away every single time we do these problems, and it ends up being a non-issue. The bigger issue today that I want to make sure that we really understand is the effect of that x. Where is it, what is it doing, and what does it mean? So to quickly summarize, just as a reminder, I'll very briefly go back to page 6, the bottom of page 6 specifically, to remind you of what x was and why it has any implication whatsoever. X is basically a way of saying, hey, we don't know where to stop taking areas. It's not clear where this function really begins and ends. The cosine function is the one that we'd be taking the area of in this problem, and the integral from 0 to x tells me that no matter what, we're definitely going to start our graph at 0, but beyond that, we don't exactly know where to stop. We know that a cosine graph looks like this, for example, so the question would basically be, well, where do we stop? Do we go from 0 to 0 and just find this little region here? Do we go from 0 to pi over 6 and find this little region here? Do we go from 0 to pi over 4 and find this region here as well? Do we go to pi over 3, which would be like another little region here? Do we go all the way to pi over 2 and fill in this space here? So that's what the question is really kind of posing to us. When x is unknown, it's basically saying, yeah, keep finding areas till I tell you when. And if we don't know what x is, that means keep finding areas forever. And we start to think, wait, how can we do that? How do we find areas forever? But that's that purpose of the fundamental theorem, is to say, no, okay, don't get carried away. You don't really have to find it forever. You can kind of go through the motions of an integral and figure out an expression that allows you to do the integral process without getting stuck in an infinite loop of doing problems forever and ever and ever and ever without having a distinctive stopping point. So that's what the fundamental theorem is. It basically saves us from ourselves. It saves us from having to do an infinite series of area problems where we just never have an end, and allows us through a loophole to kind of do the problem without officially ever finishing the job. So just kind of having that context is important, because the one thing we notice on pages 6 and 7 is the fact that x is always the unknown quantity at the end of our domain. That was something that we should always kind of make sure we're thinking about. We know where to start. At least that part is set. This problem, for example, told us to start at 0. It just didn't tell us where to end. And that's really important with the fundamental theorem. We can deal with not knowing where to end as long as you tell us where to begin. So that's going to be the thing that on page 8, I want to make sure that we start to pick up on. We need to know where to end. This integral on page 8 in question number 4 does not tell us where to end. This integral tells us to end it, or sorry, doesn't tell us where to start. I misspoke. It doesn't tell us where to start. It tells us to end at 3, but it doesn't tell us anything in the traditional format. So I'm looking at this integral in number 4 saying to myself, wait a minute, hold on. Shouldn't I be starting at 3 and ending at x? So this seems peculiar because now I'm talking about a sine graph, and I can just kind of visualize for a second what a sine graph would look like. A sine graph is the one that starts at 0. And I'll just make a quick little sketch. The traditional sine graph stops at 2 pi and has a nice little middle point there at pi. So 3 must be my ending point. 3 must be just shy of pi. So 3 is probably telling me to stop finding an area right around there. Okay, no big deal. But where do I start? Do I start like in the middle? Do I find all the areas in this section? Do I start to the left of that? Do I start maybe here and find areas? Do I start at 0 and find areas? Maybe I should go backwards. Maybe I should continue the graph to the left and find the areas down here. I just don't know. So this problem is different because we have a definitive ending point but no start. And that's the exact opposite of the problems that we were doing in the previous lesson, where we had a definitive starting point but no end. So that is something that we should notice and perhaps articulate in question letter A. What makes this expression different? The unknown limit, the unknown boundary, is now the starting point and not the ending point. That's what we need to make sure we pay attention to. Now in letter B, it's asking us, how can we deal? What do we know about integrals that can allow us to do this problem like we were doing the lesson, or the problems in the previous lesson? So this might be a handy time to think, what have we seen before? What are some rules of integrals that we can apply? And how can we adjust this so that it looks like a more traditional problem? A more traditional problem has x at the top of the integral, not at the bottom. How do we do that? Now, I'm going to give you a second to brainstorm, and I'm going to suggest, if it hasn't occurred to you already, that you consider a previous lesson, not the one that you might have done in the recent history, but a little bit further back, perhaps last week. At the bottom of page 2, a whole separate section, we had some rules of integrals. And there was one rule of integrals that we discussed that did allow us to have some flexibility with the order of our limits. We call those things limits, those boundaries of integration. But it was rule number 2. So this is at the bottom of page 2 of the new packet. And if you don't have it, you can certainly take a screenshot of these rules just so you have access to them. Notice rule 2 though. Rule 2 says that if you go from some point to another, point B to point A, that's the same thing as going in the opposite direction, just negative. You can switch the limits of integration, just make this integral negative when you do the switch. So we talked about that in the context of area. We talked about why that makes sense, but it's interesting that now we seem to have another really awesome application of this rule. I do want to switch the limits of integration in the problem that I'm trying to do, and I do need to make that switch happen in such a way that doesn't mess with my area. So it looks like this rule would be really helpful to use. If I want to switch the limits of integration, if I want to switch the order of them, I can do that as long as I put a negative in the front of the integral. So let's see if we can use that to help us adapt this strategy. That the derivative part, I haven't even talked about yet, I'll leave that there, but that the integral part can switch. So that instead of the integral from x to 3, I can call this the integral from 3 to x, which is totally allowed as long as I put a negative in the front of the integral. Now, of course, the sine t and the dt are still there. This one has the dt outside of the brackets for whatever reason, but I don't think it matters where you put the dt as long as it's there, because it's just going to go away anyway. It's part of the dummy variable. Now, let's see what this does. This doesn't really do much from an understanding perspective. We still don't know what x is. We still don't know where we're supposed to stop finding an area. But remember what you practiced in the previous lesson? How if you have one of these problems, you can kind of take a shortcut on things. This might be a great time to apply that shortcut. If it's still unknown to you why that shortcut works, we can talk about why it's going to work in a second, but let's refer back, if you haven't yet, to what you did on page 7, where you practiced the fundamental theorem of calculus. We know that when we have to take a derivative of an integral, those two operations are going to cancel each other out, and our only job, our only thing that we have to remember is that we have to plug in the x, the unknown limit of integration, into the dummy variable spot. But if those two things cancel out, our only real step is to recopy the function itself and just replace the x. So if I have one of those problems, I can totally do this. The derivative will cancel the integral. Technically, it also cancels the dt. They all kind of cancel out in one big fell swoop. And it looks like I'll still have a negative, I'll still have the sign, and instead of t, I'll replace it with an x. According to what we saw in the previous lesson, that should be the final answer from the fundamental theorem of calculus. That was the beauty of that shortcut, is it made these problems so much easier. Now, if your head's still swimming a little bit and you're like, I just don't understand, why is that working? Why does that do what it's going to do? We can look at it in a bit more depth in question letter D so you can appreciate what that shortcut has accomplished for us. In reality, that shortcut saved us a lot of time, because this is what we would have really had to do. If we really wanted to do this problem for real, I'll recopy what we had. We had negative integral from 3 to x. Remember, we switched the order of things. And then we had sine t dt as its function. So if I really wanted to do this, like for real, I would first do the integral. I would do the derivative part afterwards because it's outside the brackets. I'm going to handle what's inside the brackets or parentheses first. Now, the negative is just going to be there kind of minding its own business. And I would have to do the integral of sine t dt to be able to kind of finish this problem. So I'm going to do that right now. And I'm just going to make this happen quickly. The integral of sine is negative cos t evaluated at x and 3. So that's still just basic rules of antiderivatives. I took the antiderivative of sine, that's where I got negative cos, and then I'm plugging in my limits of integration, same way as I always did. The extra negative, and I'll highlight it just so you can see where it's coming from, the extra negative is this one I'm highlighting yellow, and that came from, again, that rule of integrals that I pulled from the previous lesson. So, just kind of finishing the job here, I just have a lot of stuff to keep straight. It's not really like any of this is new, it's just stuff I have to keep straight. I'm going to keep that negative there, just in case. I don't want to distribute it because remember, this negative is part of something that's getting evaluated, but this negative isn't necessarily, so I don't want to mix them up. If I plug in, I'll have negative cos of x minus, and then I plug in again, negative cos of 3. So this is fun. I know that cos of 3 isn't going to be very much fun to actually evaluate, so I'm probably not even going to bother. I have derivatives, still haven't done anything with that. Now I have negative and then a quantity, so I'll bracket that off again. The negative is still going to just go along for the ride. Well, let's clean this up a little bit. I have negative cos x, can't do anything with that. Minus negative cos 3 becomes plus cos 3. Again, cos 3 is not really a nice number, so I'm just going to have to deal with that. Now if I clean this up a little bit more, just to be super safe with all of the negatives that I have, negative cos x becomes cos x. Negative cos 3 becomes minus cos 3. And I would say to myself, cool, I'm done, except, I still have d dx outside. That means take the derivative, but no worries. Derivative. I can do derivatives. Derivatives are fine. Derivatives are my happy place. I can definitely do derivatives at this point because that is way easier than what we started. So the derivative of cos x, that's negative sine x. Now cos 3 is a constant, so the derivative of a constant is just 0. That means my answer is negative sine x. And, not coincidentally, that's what we predicted minutes ago when we applied the shortcut from the second fundamental theorem of calculus. So hopefully just comparing these two processes makes it easy for you to appreciate why the second fundamental theorem of calculus is so helpful to us. It saves us the process of going through all of this work. And if all of this work still makes more sense to you than the second fundamental, that's fine. You can do all of this work as long as you know how to take the integral and then take the antiderivative, but there's a lot to chew on. There's a lot to make sense of. So that's why you just kind of have to be careful and use your best judgment. We're going to try to appreciate today the fact that the second fundamental theorem of calculus makes so fast these problems, but it is a judgment call on your part. The sacrifice that you never want to make is speed in favor of understanding. If you really don't understand what you're doing, going fast is useless. So that's why it can be helpful to really chew on these ideas and make sure that they make sense before you start taking liberties with shortcuts like we did in letter B. Now, just to make sure, in the next video we're going to talk about another extension, another application of the fundamental theorem. So before you go down to the next video, take some time to digest what just happened in page 8. Specifically, the fact that we needed to switch the limits so that the unknown was at the top, and it involved using that negative. Make sure that you're keeping track of that, because in a few examples on page 9, you're going to end up seeing that effect, and I definitely want to make sure that you have that idea fairly well in hand so that it doesn't confuse you when you have to do some problems by yourself.